Thank you, Claudia, and great to hear about all the cool upcoming talks we have lined up for you all. So please feel free to drop by to all of those talks, and we'd be very happy to have you. But today we have Jean-Karime Hériché giving us a talk at our data path. So Jean-Karime is a scientist in computational support at the Cell Biology and Biophysics Unit at EMBL in Heidelberg. JK, as we call him, that changed quickly, has been involved in all the way from microchip screens to the latest pipelines for data analysis in the cloud. So it's really like a whole breadth of things that he's covered over the years. Currently, his team is specializing in data analysis and integrative data mining, as well as data management and data release, as well as training is an important part of what they're currently working on. And he is very much involved in the European Open Science Cloud, including the eosc Live Cluster project, and has been actively contributing to some of the demonstrator projects for eosc Live as well. And well, I don't want to take any more of your time, so I would really very warmly welcome JK, and please take it away.
So I won't introduce myself, but I want to give you a little bit of background on where we are coming from for this virtual desktop for image analysis. And I've changed the title a little bit to point out that this is all happening in a web browser, but give you some more details. So the background is you probably have heard about the European Open Science Cloud, but for those who haven't, it's an initiative from the EU Commission to promote open science, but also this is part of a wider program, which is the European Single Digital Market, and it's supposed to also be some sort of precursor for it, or lead the way for further development. But the idea is to give access to resources and implement the FAIR principles, not just for data, but for tools. And by tools, we mean software, workflows, all kinds of computational resources. And to promote the reuse of data and all digital objects like software, workflows, and so on, and of course papers. And this is very important for the Commission because they basically want to get more for their money. At some point, they have realized that they are paying billions in for public research, but there is only less than 15% of the output that is actually made publicly available. And in that context, there is the cluster project eosc Live, which is a consortium of the biomedical sciences research infrastructure. That means basically Euro-BioImaging, EU Open Screen, Instruct, and so on. And roughly what the project is about is to start working on implementing eosc, so the European Open Science Cloud, for the life sciences or for the communities in the life sciences. And what this implies is that we are going to be pushed towards new ways of working with computational, remote computational resources, because the cloud is basically, as someone said, the cloud is just someone else's computer. So how do we do this, especially for image analysis? And that has a few challenges, and we started thinking a little bit about it. And so, of course, a lot of the image work that we see at EMBL, but also elsewhere, is interactive. And we are, as we do this work, we also use multiple tools. I mean, by that sometimes you start from doing the segmentation, for example, in Elastics, and then you want to use a Fiji module or plugin, and so you move between all these tools. And all these tools that are most commonly used are not cloud ready and not composable. By that, I mean that you can't easily pass from within one to the other, automate the switching from one to the other. You just have to have these manual steps. And in addition to this, they're also generally difficult to install in remote settings, not to mention sometimes also locally, especially when GPUs are involved, which probably most of you have had that experience trying to install any kind of deep learning or related library. And people have started working on bringing image analysis to the cloud, but they've done it piecewise, which means that the solutions are not interoperable. So you may have a Fiji implementation available in the cloud, but then you can't go from it to Elastics or to Cell Profiler unless you maybe have some specific plugins, and even that is not always working well. But what works for most people in the settings that we are familiar with is basically a powerful desktop workstation. And so, going a little bit ahead of this, our idea generally was to see how we could replicate that experience. And one of the use cases we had in mind for doing this is support for facility visitors. So you imagine you have visitors coming to your facility. They generate 20 terabytes of images. Now they return home, but they don't have the storage capacity or maybe the compute capacity for dealing with that data. So the facility wants eventually to support them, but then they can't keep people around in the facility at the local workstation for 6 months or a year or whatever the time it takes to actually process and analyze the data. So in essence, we have the image data stored somewhere, accessible from the facility, but they should also be accessible, and the compute should be also accessible to the visitors once they're back in their home institution. So for this, so as I said, we wanted to replicate the workstation experience in a remote setting. So for that, we want to leverage the remote desktop technologies, but we don't want a dedicated local software, which will again cause issues with installation and maintenance of versions. So we want to provide access in a web browser. Everybody has a web browser on almost all their computers. So that's basically solve the local installation problem. And then if we can put all kinds of image analysis software in that desktop, then we would be set up basically with a powerful workstation that basically works in your web browser. And that basically is what is the Bioimage ANalysis Desktop, or BAN for short. I want to say first that we didn't start from scratch, but we actually based all of this on the work done in Australia, particular for the Massive facility, where they also developed virtual desktops, and then that run in their own cluster. And so to replicate that, we went to an OpenStack cloud environment, and we use for the aficionados infrastructure as code, which means essentially we're deploying this by writing scripts. The key features that our setup has are basically if each desktop that you start is run as an HPC job. So that's basically we have in the background at the back end a cluster, a compute cluster, and each desktop is a job in that compute cluster. And one of the consequences of this is that desktops are user configurable. Just like HPC jobs are configurable, you can specify the resources that you need in terms of number of CPUs or GPUs, the amount of RAM, You can imagine more that those are the main ones we offer at the moment. And in here, to deal with the problem of installing many many pieces of software that are sometimes incompatible, we run and we package and run everything in containers, in that case, Singularity containers. So each application is isolated, and that solves a lot of problems in terms of compatibility, setting up things that have conflicting requirements, for example. And finally, the user home directories are persistent, which means that if you when you kill your desktop after a session, or when you're done using it, whatever you've saved in your home directory will be there the next time you start a new desktop. So with this, I would just go a little bit more into the details. So I won't bore you with very deep technical details. Feel free to ask. But so the way this works is kind of split into three layers. The outside facing web layer, which is what interacts with your web browser. An intermediate authentication layer that basically deals with the accounts, user accounts, and basically the persistence layer, which is basically our cluster, which we run using Slurm. Our cluster at the moment consists of 3 large GPU nodes. So each node has 8 GPUs. And the way we've configured it is that we keep one GPU for virtual GLs, that is hardware graphics rendering, and 7 are dedicated to computation. And on those machines, each one has 56 CPUs and 483 gigs of RAM. Beside those, we also have purely CPU nodes for desktop, for example, that don't need GPUs, and they have 48 CPUs, 244 gigs of RAM. On the nodes, we have mounted the NFS volumes. So part of those are for storing the application containers, so the Singularity containers, and the other part is for the user home directories. We can also customize sometimes part of it for courses. I'll come back to that later. And then recently what we've added is actually a high performance file system, because now what we've realized is that we have a system that also allows to run typical cluster jobs. So actually we now have a hybrid system where you have a desktop, but from the terminal you can actually run HPC jobs or using the Slurm batch scheduler directly, and we found that it's actually useful. It was useful also for a recent course. On the authentication layer, so we have a key cloak server that communicates at the moment with Google, which we use as identity provider. So all that's needed to get a desktop is to have a Google account for now. Then there is an LDAP server that manages those accounts. So if you connect for the first time, we will have an account creation step where it will basically create all the sub accounts, like the Slurm accounts, the home directories, and various bits and pieces, and then basically send you back an email when it's ready, telling you that now you can log in with your credentials. And of course, there's the web server, which serves mostly the Guacamole application, which is what renders the desktop in your browser, and some proxy intermediates. So just now a few screenshots to show you how it looks. I've learned long ago not to do live demos during seminars, because that's always when they break. So once you've logged in, you're presented with this page, and that's where basically you can configure your desktop. So choose the number of CPUs, the memory, if you want GPUs. I think at the moment we have limited the number of GPUs to 1 per desktops, but nothing prevents us to actually let you use all 7 that are on a node. You can choose or set the resolutions to adapt it to the size of your monitor. If you're working with a small monitor or large one or laptops, that might be useful. And then the time you want to use that desktop. So it defaults to 2 days, but you can go up to 2 weeks. And after that, the desktop is automatically killed. So then once you've chosen your settings, you just click on launch. And that's after a few seconds, your desktop should be ready. And this is what you get. You have a timer that tells you how long it stays. It's still as before it's destroyed. You don't have actually to go to the desktop. If you like more command line stuff, you can directly SSH into your desktop and just interact via terminal. And the stop desktop button is just for basically killing your desktop. So it kills the Slurm job. So you can click on go to desktop when it's ready, and then you get a regular Linux desktop. So here I've shown already some Fiji work. So Fiji is open with an image. I'm showing you some of the tools we have here on the left in the menu. So different versions of Cell Profiler, Fiji, Napari, all kinds of things. And we're happy to add things on demand. So if you need something there, we're happy to accommodate. We also have some deep learning applications, so that's also very, very well appreciated. And so they were used, as you can see here, for some deep learning courses. We have basically one set of notebooks or kernels based on Keras and some based on PyTorch. And if you've ever tried to install those things on the same machine, you know how painful it can be. There's also Nime and RStudio for people who want to work with those. One thing that's important is data access. And what we recommend, especially for working with large data set, is to have your data in S3 buckets. And so we have a tool here that connects to your S3 buckets and basically generate a folder for it in your home directory. So this is a fake mount. So every operation that happens in that folder is actually happening in your bucket. And so it's not a real folder, and inside are not real files in your desktop. They are still in the bucket. And the reason we're doing this is basically all those legacy image analysis applications don't know anything about cloud and about cloud storage in particular, although some are being retrofitted with this. But so then all they know about are files. And so we present your bucket as a file system, and they can interact with it. You can also access OwnCloud or Nextcloud storage. And we have also a NextNav client, although we haven't really tested it. We know it kind of works for the basics, but we don't have use cases that allowed us to test it. So we launched Band about less than a year ago officially. So that was just shortly before Christmas last year, and we already have 300 users or close to. And that's what surprised us, is that it became very popular for courses almost right from the start. So it was actually selected for deep learning courses twice within basically a month already of being officially launched. It's used for EMBL courses, official EMBL courses. In particular, we had the deep learning for image analysis course. We have had EMBL practical courses, the recent current methods in cell biology, and this summer the advances in cryo-EM and 3D image processing. We had the Swiss Image and Data Analysis School, and at the moment, over the past few weeks and in the near future, the Neubias Defragmentation Training School. And those are only the ones we know about, because there is nothing that says you have to ask us to use the band. So if you actually want to use it without telling us, you can. The advantage of telling us is that we can reserve resources for your course. So if you tell us we want to have 20 desktop with GPUs, it's much better to reserve them. And anyways, we can actually accommodate at most 21 or 24, because that's the number of GPUs that we have available. We have ideas, of course, for further developments, but some of them are actually going to happen. So the one of the next one, if things get out of limbo, is this life science login. So it's a federation of login for academic institution, which means that instead of logging with your with a Google account, you could use your home institution credentials, provided, of course, that your institution is part of the life science login federation. And basically, this is a part of the core of EOSC, also to federate the identity, so that basically you can access all the services using your home institution credentials. So that's, at the moment, there is a little bit of legal limbo about implementing it, but once this is sorted, that's going to be in place. I mentioned configuration options. So you've seen we offer already a few things in terms of mostly the hardware side, but we could also go further and offer disk space. At the moment, the home directory is not limited, so we don't have quotas in place. But maybe as the number of users grow and they start keeping too many files or too much data in there, we might start enforcing limits, and we can then provide users with how much they want. We can also offer the configuration in terms of available software. So at the moment, everything is available by default, but as the list grows and maybe people have different focus, we could basically split all that and make it basically an a la carte selection. And of course, I've shown you one type of desktop. So this is a Ubuntu/Mate flavor, but we could eventually offer to make it look like Windows or Mac OS, if that's what you're more familiar with. But that's more like cosmetic, so probably not a high priority at the moment. Something we want to look into is how to share sessions. So at the moment, when you open a desktop, you're the only one that can see it. It's a little bit tricky to make them shareable if you want to be more than one person working in them. At the moment, there is a bit of a workaround when you use Zoom. That's not been fully tested, but at least you can share a screen and show someone else what you're doing in there. But yeah, there's possible improvement there. We want to expand on the data access options, maybe things like all the storage like Dropbox and other things. Add some workflow management system, especially because now we've made the cluster accessible from the terminal, so you can have access directly to the Slurm command. So you could run typical automated workflows from your terminal also in there. And something we might want to look into at some point is to further expand on the interoperability with other cloud services. So we could at least it's not inconceivable that we could exchange tokens, for example, with the EGI Jupyter Notebook service or with public Galaxy servers. So those would be things that we could do. With that, I want to conclude with some acknowledgements and thanks. So this is work supported by eosc Life and by EMBL IT Services. EMBL IT Services would provide the OpenStack environment, so as part of the DEMD cloud, inside which we run all this. But the key person here is my collaborator, Yi-Sun, who is really a talented engineer and developer who's basically set most of all of this. So I really want to acknowledge his contribution here. And with this, I'm happy to take questions.